An extremely handy result, the gradient is orthogonal to level curves. Anything of this form is a level curve, or level surface, depending on the dimension. You can always make one by throwing everything to one side of the equation and calling it f. Now it's a level curve. The gradient is always going to be orthogonal to a level curve. Let's prove it. Depending on the dimension, it's called the level curve or a level surface. Special case, z is a function of x and y. So it's like the xy plane got lifted up as a surface, and we're going to intersect it with z equals a constant. The xy plane lifted up. Two equations make a curve. Since z is replaced with a constant, it's a function of x and y only, so I can graph it in the xy plane. Now it's called a level curve. Parameterize, take any point, and take the tangent vector. X and y are functions of t, because the vector form r points to a point on the curve, which is parameterized in t. We're in the xy plane, z is 0, so z prime is 0. Plugging the parameterization and taking a derivative. Chain rule. The gradient dot r prime is 0. The gradient is orthogonal to the level curve. Going up a dimension, given any surface, I just throw everything to one side and call it f. Grab any point on the surface and any curve in the surface going through that point, and take a tangent vector. Plugging the parameterization into f, everything's a function of t now. Take a t derivative and chain rule. Gradient dot r prime is 0. The gradient is orthogonal to the level surface.